Good afternoon. Let us start our lecture. So far we talk about random variables, which represent a set of values, and each value take the random variable takes that value with certain measure to measure how likely it takes that value. So it's a random variable. You can also treat it as representing an individual in a population. So usually it will be represented by a function, I call it f of x, and for discrete random variable, it is called probability function, and for continuous random variables is called probability density function. All right, so this function tells you everything about the behavior of the random variables. Consists of the range of the x value, as well as how the probability functions behave. So if we want to have just a few numbers to summarize the behavior of the distribution of this random variable, we look at this expectation. So an expectation of a random variable is a number, is a constant, is equal to all the x times the corresponding f of x. All right, and then sum them up for discrete case, and is equal to integrate x f of x dx for continuous random variable. All right, so basically it is sort of like a weighted average. That means each value weighted by their chance. The bigger the chance, they contribute more to the expectation of x. All right? So, in particular, the expectation of a function of a random variable. All right? A random variable, if you take a function, again, it will be a random variable. So, for a random variable, it means it takes possible more than two values and with certain probability. So this is a random variable, so it makes sense to talk about expectation of the random variable. And this one, all right, okay, if I call this y, so to find this expectation is the same as finding expectation of y if I call this y. All right, so you may have to work out the distribution of y, which is not an easy task in some situation. So, but if you're just interested in the expectation of gx, then what you have to do is just replace all the x in the place of x. You just work out the f of x, the gx, and then sum them up, or integrate gx f of x dx. All right, this is for discrete, and this is for continuous. So basically, just have to replace the x by the function of x itself. So that is the expectation of the gx. So in particular, gx, a particular gx is the x minus mu square, where mu is the expectation of x. This is to measure the square of the difference between x and mu x, and what we expect about this number. If this number is small, that means the x values are very close to the mean. If this number is big, expectation of gx means this one is big, then that means the variation is huge. All right, because it means that x is quite far away, or it's likely that x are far away from the mu if this number is large. And this is called variance. And the square root of it is called standard deviation of x. Another special function is g of x. Let me continue. G of x equal to x to power k. So in this case, we have measured what we expect about if I take the kth power of the x values. So this one is called kth moment. So it basically measure how the values, each of the value deviate from 0, and then you raise to power k. All right? So a third type which is not in the notes is that when gx takes the value x minus mu to power k. So the variance is a special case with k equal to 2. All right? This one with a name for it, x minus mu to power k, is called kth central moment. Because now we have measured not the difference between x from the 0. 0 may not be the center. All right? But while we measure x deviate from mu, mu is considered as the center of the distribution. All right? So these are the few typical form of g of x that we may interest. All right. So let's continue with our chapter 2. Okay, so let's look at an example. Now, in this example, we are given the probability function in a table form. All right, for discrete case, we can have a two approach or two way to display the f of x, the probability function. One is given in a formula, while the other one is given in a table form. So in this case, you can see that x takes four values, -1, 0, 1, and 2. And the corresponding probabilities are 1x, 2x, 1x, and 4x. So make sure that all these probabilities or probability function add up equal to 1. This add up equal to 1. And each one is bigger than 0, bigger or equal to 0. So what happens if x equal to -0.5? What is f of x then? Since it's not given here, so f of -0.5 is equal to 0. Remember, for discrete case, this probability function basically means the probability of the random variable x takes the value x. So in other words, here, if we are asked what is this, is the same as probability of x equal to -0.5, which is not in our table, so it means the probability is 0. All right, so we are asked to find the expectation of x and the variance of x. So now, without this probability function, so if you just take the average of these four numbers, all right, it simply means that you're working on a probability function with 1/4 for each of f of x. But now it's not 1/4. 1x for the -1 and 1, while x equals 0, the probability is 2x, while probability of x equal to 2 is 4/8. All right, and we are also asked to find the expectation of y and variance of y, while y equal to x squared plus 2. Now this is a function of x. All right, it's a function of x. All right, so applying the formula, all right, expectation of x is the x times the corresponding probability function and sum over all the x. So it's equal to -1 times 1/4, 0 times 2, sorry, 1x, and plus 0 times 2x, plus 1 times 1x, plus 2 times 4x. So these are the x values. While all these are the corresponding density probability function. All right, so it turned out to be 1. And while for the variance of x, so according to the definition, is x minus the expectation of x, which we work out to be 1, and square it, and times the corresponding density, so probability function, and sum over all the x. All right? So it's x minus mu x, you square it, and similarly here is x equals 0 minus 1, square it times 2x, and plus the rest. So the variance is 5 over 4. All right? Okay. And how about y? Oh. So we'll show this later. The variance of x is equal to the expectation of x squared minus square of the expectation. Now these two, let me repeat again, these two are not the same. This means that you have a random variable, which is the square of the random variable x, and then you find the expectation. This one, you take the expectation of x first, and then square the expectation, square the constant. Here is the square of the random variable. Okay, they are usually different. All right? So this is a formula that helps us to find the variance of x. So instead of working on x minus 1 square f of x, sum over all the x, which is the variance of x, now I work on the expectation of x squared, which is just x squared times f of x. X squared times f of x, and sum over all x. All right, so that's what we're going to do. And it turns out to be 9/4. And the variance of x equal to 9/4, which is expectation of x squared, minus the square of the expectation, which is 1 square. So the answer again is 5 over 4. Usually, this formula is easier to compute than the definition. X minus mu x. All right? So that one is a little bit more complicated. Think of it. Here, you have, from the computational point of view, you have to find the difference, x minus mu, and then you square. So that means you need to find the difference and then square. While for this one, you just have to square each of x. You don't have to find the difference of x minus mu. You just square the x. So, much less work. But at the end, you still have to work out this part, provided that you have to know what expectation of x. Okay? So even if you don't know, you have to work it. The number of steps or number of computation steps are smaller. All right. How about this new random variable y? And what's the expectation of y? And what's the variance of y? Now there are two ways to do it. One is to treat this y as a new random variable, get the probability function of y. Get the probability function of y. Okay, so sorry. Okay, I want to know what is the probability function of the random variable y. So ask yourself, what are the values of y? So look at it, when x equal to minus 1, 0, 1, and 2. So y takes the value 0, 1, and 4. Y takes the value, when x equal to minus 1, it is 1 plus 2. So it's 3. All right, okay. Maybe let me write here. Y. So y equal to minus 1 square plus 2, so it's 3. 0 square plus 2, so it's 2. 1, when x equal to 1, then y equal to 1 square plus 2, so it's 3. And when x equal to 2 is equal to 2 times 2, 4. 4 plus 2, 6. Am I right? Okay. So these are the corresponding value. So when x equal to 0.5, for example, then what is y? Y is equal to 0.5 squared plus 2. So maybe 2.25. All right? But we don't bother about it. Why? Huh? Why I don't have to compute when x equal to minus 0.5 or x equal to 0.5 and the y value. Why I don't have to compute it? Because it's too many for us to compute? No. Because the chance that x equal to 0.5, what is the probability? What is the value of the f of x? f 0.5. 0. The probability is 0. That means x will not take the value 0.5. So if x does not take the value 0.5, why bother to calculate y when x equal to 0.5? All right? You can compute it, fine. But it does not contribute to our probability function of y. All right? So next step is to calculate f of y. So in fact, summarize it, y only take 3 different values, 2, 3, and 6. What is the chance that y equal to 2? So y equal to 2 means that x equal to 0. So it is 2 over 8, f of y. While y equal to 3. Y equal to 3 means that x, okay, probability of y equal to 3 is equivalent to probability of x equal to minus 1 or x equal to 1. So these two, if x take minus 1, x cannot take 1. So they are mutually exclusive. So you have to add up these two probability, right? So it's equal to 1x plus 1x. So it's equal to 2x or 1/4. So it's 2x. All right? And finally, the last one, if you believe you don't make any mistakes, then this is 1 minus 2x minus 2x, so it's 4x. Or alternatively, probability of y equal to 6 is equivalent. That's why you need the equivalent event. It's equivalent to x equal to 3, which is 4 over 8. All right? So, then you can work out the expectation of y and the variance of y based on this probability function. All right? This is one way to do it. That means you treat this function of x, call it y, which is x squared plus 2, work out the probability function, which needs the value of the y. In this case, it's 2, 3, and 6, and the corresponding probability. All right? But what I gave you in the notes, we use another approach. Basically, just treat it as a function of x. So it is gx times f of x. All right? And then sum up over all the possible x values. So this is how we get 17 over 4. So that's the expectation of y. If you use this probability function, you should get the same answer, 17 over 4. That means 2 times 2x plus 3 times 2x plus 6 times 4x will give you the same answer. Okay, how about, okay, in fact, we can also work it like this. This one, instead of working from a formula, I work using the properties of expectation. It's like this. Expectation of x squared plus expectation of 2. But 2 is not a random variable. 2 is a constant. So what do you expect? 2. 2. So what you expect is the same as the value of that constant. So it's 2. So you just have to get back expectation of x squared. We have already done it. 9 over 8. 9 over 8 plus 2. All right? This is 9 over 8 from part A, and this is 2, so the answer is 17 over 4. All right. So this seems to be even easier, all right, because we have already worked out expectation of x squared. Now, variance of x. Okay, so we treat this as a function of x minus the expectation of the function of x, and square it times the corresponding probability. All right, so that is how you get the variance of random variable. Okay, so variance of a random variable x is equal to sum of x minus the expectation of x square times f of x. All right, so if we replace this by gx, then this one you replace by gx, this one the expectation of gx. All right, this one we still keep using the probability of x, right? So we just work out the variance of y is 51 over 16. All right? Okay. So we can also apply the formula variance of a random variable equal expectation of y squared. So in that case, we work out expectation of y squared. So this is y squared, all right? And turn out to be 170 over 8, and then minus the square of the expectation. So this is the expectation of y squared, and this is the square of expectation. So it's 51 over 16. Okay? Now, later we'll find out, but I have this question. Variance of, we have expectation of y equal expectation of x squared plus 2. How about variance of y? Does it equal to variance of x squared plus 2? All right, I give you the answer at this point. Later we'll see why. Okay, this one is wrong. Because variance is defined as expectation of y minus expectation of y, square the whole thing. So it is expectation of a square of something. It's not expectation of y. It's expectation of square of the difference of y minus the mean. All right, so this is not true. This is true. Expectation is a linear operator. Okay, so now let's look at an example for continuous random variable. The PDF is given in this form. So the PDF x, f of x, all right. So between 0 to 15 is up and then come down from 15 to 30. So this represents the PDF. 0 all the way, up, down. So the area under this curve or this triangle should be 1. All right, so expectation of x and the variance of x. So expectation of x, by definition, integrate from minus infinity to infinity, x f of x dx. Remember, I repeat again and again, make sure that you multiply the x. Don't just integrate from minus infinity to infinity f of x dx. That will always give you the answer 1. And also pay attention, f of x does not equal to any of this expression throughout the range, minus infinity to infinity. But this one, you have to separate into 4 parts, in fact. Minus infinity to 0, 0 x times 0 dx, plus from 0 to 15, x times x over 225 dx plus from 15 to 30 x times 30 minus x 225 dx plus from 30 to infinity x times 0 dx. All right, because the PDF defined over 4 different regions. For the 2 regions from minus infinity to 0 and from 30 to infinity, the PDF is 0. So this gone. The integral is 0. So therefore, it disappears. So we do the integration. So I left the integration part for you to look at it. So the answer is 15. So the expectation of x is 15. All right? All right. So how about the variance? So this time, instead of looking at expectation of x squared, instead of looking at expectation for x minus, what's the number? 15, right? X 15 square. So instead of working on this one, I work on variance of x equal expectation of x square, then minus 15 square. This is the square, this is the expectation of x. So I do expectation of x square. So integrate x squared times the f of x. All right? So it's just a polynomial, then so you work it out. So it's 262.5. So therefore the variance equal to 262.5 minus the square of 15 and turn out to be 37.5. All right. Now, so here's another example. So suppose x, let me repeat. You must know what the random variable represents. What does it mean? All right? So when you do a tutorial problems or tests or exam, please just have to define what are the random, what are this meaning of all these random variables. So in this example, x is a random variable, denote the amount of time for which the book is checked out. All right? So it's the amount of time and by selected students. And suppose, now then the next question is, after you have defined what is x, the next one is what is the PDF of x? Or probability function of x, depends whether it's continuous or discrete. For this case, because we're talking about the time, so time usually is continuous. All right, so f of x is given by x over 2 whenever x is between 0 and 2. And it's 0 otherwise. All right? Why 2? Because the book is have to reserve for 2 hours. You can only check out for 2 hours. All right? You're supposed to return it within 2 hours. So that's why the definition here up to 2. All right? Now, whenever you see something like this, the PDF, it's supposed to be a PDF. Make sure that the 2 basic properties of PDF is satisfied. First one, the function must be greater or equal to 0. F of x is bigger or equal to 0 for all x. So in this case, it will be 0 if it's outside this range. Within this range, it is x over 2, and x is positive, so x over 2 is positive. So the first condition satisfied. Second one, we cannot see it right away. You might have to do the integration. That means make sure that f of x integrate from minus infinity to infinity dx equal to 1. But this one does not equal to minus infinity to infinity 2x dx. If you do it like that, you will not get 1. And what's wrong with it? Because the PDF does not equal to 2x for x from minus infinity to 0 as well as from 2 to infinity. All right? So you can only integrate this one from 0 to 2. Okay? The other range of x, the probability density function is equal to 0. All right, it should equal to 1. All right, so we compute expectation of x, variance of x, and so part A, part B are straightforward, so you can do it. Now, we have a function of x. which is x squared. This is supposed to be the amount of money that you charge for borrowing the book. So the longer you check out the book, the more you have to pay because it's x squared. All right? The longer, the bigger the x squared value is even bigger. So we are supposed to find the expected charge. All right? So it's equal to, okay, part C. All right? It's just expectation of x squared, which we already have done it for this example. So it's equal to 2. Now, but if the charge, let's say I change it, h of x equal to x cubed, then this one is expectation of x cubed, then you have to integrate x cubed from 0 to 2, x over 2 dx. So you have to work this out. All right? So it depends on how you define it. But since h of x is given to be x squared, which we already done it when we compute the variance of x, so it saves us some work. All right? Okay, properties of expectation. The first property, expectation. I have to emphasize, variance of x is an expectation of this function. So you have to be careful. Expectation of this function, which is supposed to be expectation of x squared minus 2 mu x plus mu square. Right. So my point is variance is an expectation, but it's not expectation of function x. It's not expectation of x, but expectation of a function of x. All right? So in fact, it's equal to this whole thing. So if you are working on the expectation of a new random variable, how do you describe this new random variable? Ax plus b. A and b are constants. X is the random variable. All right? So this, in fact, is a linear function of x. So if I call it y, call this y, then y equal to ax plus b. This is an equation of a line, a straight line. So we call this a linear function. In fact, this is a linear function. So if expectation of y is a linear function of x, then it's equal to a times expectation of x plus b. That means if you want to take the expectation of a new random variable, which is ax plus b, it's the same as you take the expectation of x first. Take the expectation of x first, and then multiply by a, and then add b. All right? So you have to understand these two. They're the same. We can prove it, but they have different interpretation. The one on the left-hand side, expectation of ax plus b, is the expectation of a random variable, which equal to ax plus b. So in other words, you multiply a to x first and then add b. After that, then you take expectation. That is the sequence. All right? It can be shown that this sequence is the same as you find the expectation first. Instead of finding the expectation last, you find the expectation of x first, multiply by a, and then add b. These two are the same. All right? This will be very useful. All right, so we just prove for the discrete case. For continuous case, you have to prove it through integration. So the idea is the same. Expectation of ax plus b equal to the function of x times f of x, sum over all the x. Then this part, I can rewrite this as summation ax times f of x plus b times f of x. That means each general term, I break it into the sum of two terms, ax, f of x. All right, so you can think of it like this: ax1 times f of x1 plus b f of x1. This is when x equals x1. Then plus ax2 f of x2 plus b times f of x2, and so on. All right. So what I'm going to do is to group this together. So it's just like I take all the ax f of x and then take all the b f of x, sum over different x. All right. This represents a general term. Different x give you different ax f of x. So I just grab all this ax f of x, ax1 fx1, ax2 fx2, ax3 f of x3, and so on, group together. So I put it like this. Then, so it's like this, right? So next, look at this sum. Each term has a common factor, a. Is x a common factor? Common factor means that this factor appears in every term. A appears in every term. X, X also appears in every term. No, X is the running subscript. That means it keeps changing. Different terms have different X values. So X is not common to every term. All right? So only A. So I bring out A as a common factor times summation X f of X. Similarly, this one I take out B. So it's sum of X f of X. All right? But what is this? This is our expectation of X. And what is this? What is this? 1. That's the definition of the probability function. Sum of f of x over all the x value should be 1. Sum of all the probability should be 1. Now, this is a very important techniques that we used. So remember, sum of the probability function of any distribution should equal 1. The definition of probability function. Or integrate for continuous, then integrate x f of x dx is also equal to 1. All right? That's for continuous random variable. So I have a times expectation of x and plus b. So we prove the property of this expectation. All right? This one equal to expectation of x. This equal to 1. All right, so in particular, if you put b equals 0, then expectation of ax equal to a times expectation of x. If we put a equal 1, then expectation of x plus b equal to expectation of x plus b. So it's straightforward, but here is the interpretation. It means that if you have a new random variable, which is to multiply x by a constant, then you expect your expectation is just multiply the expectation of x by a. That means whatever you multiply to x, the expectation also multiplied by the same factor. Also, if you add to each x value by b, by a constant b, all right, then your expectation of this new random variable should be the expectation of x plus b. In general, you can prove it, but we don't. It basically, if you add up all right, a bunch of terms, each term is a constant times a function of x. Different function. That's why I use g1x, g2x, up to gkx. We have 8 different functions of x. That means I have k new random variable. So I multiply a1. So the same, this is equal to a1 times expectation of g1x. All right. So what it means is that if I create a new random variable, which is the sum of a1 times g1x plus a2 times g2x and so on, all right, so create this new random variable and find the expectation. It's the same as I find the expectation of each of this function of random variable x first. So I find expectation of x, expectation of g2x, and so on, and then multiply by ai, and then sum them up. Okay? Okay, this is the formula that we just used to find the variance of x. So So here is how we prove it. So remember, this is again, I have to stress or emphasize, variance of x is equal to expectation of a square of something. Square of something. So you must expand it. All right, so it becomes expectation. This is just a minus b squared, which is equal to a squared minus 2ab plus b squared. A is x, b is mu x, so it's equal to this. All right, look at these three terms, sum of these three terms. The first one is x squared, is square of the random variable x. The second one is minus 2 times mu x times x, then plus mu x squared. So according to the property 1, I can rewrite this as expectation of g1x minus 2 times expectation of g2x plus expectation of g3x. All right? All right. So I just copy this. This one, remember what we just discussed, expectation of ax is equal to a times expectation of x. So I can bring out this and this. Remember, mu x is a constant. It represents the expectation of x. It's a constant, it's not a random variable. So I bring these two out. So finding expectation of x. And the last one, because this is a constant. So for a constant, what do you expect? Must be that constant. So it's equal to mu x squared. All right, but what is this? This is mu x. So in other words, the second term is minus 2 mu x squared. So this is the final answer. All right, this is our square of the expectation. All right? So this is how you get this formula. And this formula is supposed to be easier to work with. We call this computational formula for the variance of x. So if you get expectation of x squared and also get the expectation of x, that means you need this too. But it's not the difference of the two. It's this one minus the square of expectation of x. Oh, here comes the thing. In general, this is not true. So I just have to emphasize that. Expectation of x squared, in general, does not equal to the square of the expectation. All right, property 1. Simply state that you multiply a constant to x and add a constant. The expectation is the same as you take the expectation first. All right. Here, you suppose square the random variable x and then take the expectation, which in general does not equal to take the expectation and square it. All right. In general, this is not true. Okay, so this is another useful formula. It looks strange. Variance of a new random variable ax plus b is equal to a squared times variance of x. So this one does not equal to a times variance of x plus b, because variance of x is not expectation of x. It is expectation of variance of x is not the same as expectation of x, so you can not use it. All right, and you can only do this expectation of x minus mu squared. This is the function of x. All right, so we have to work it like that. So now here's the proof. Now this proof that I have here, I make use of the formula. Remember the formula? Variance of a random variable. Okay. X is equal expectation of x squared minus the square of the expectation. So I do the same thing. Variance of this, so I square this one and take expectation. Minus taking the expectation of this ax plus b first and then square it. So look at this. So what I'm going to do, I'm going to expand it. So this one, expand it, is a squared x squared minus 2abx plus b squared. And expand it before you take expectation. While this one, I take expectation. So this expectation of ax plus b becomes a times expectation of x plus b. All right? So, after you take expectation, this is a constant. It's just a square of a constant. The constant is a times mu x plus b. Remember, mu x is another notation or means expectation of x. Okay, how about the first expectation? So now I apply the property of the linearity of apply the property of the expectation. So this equal to a squared times expectation of x squared. All right. This one, 2ab, take out expectation of x and then b squared. Because expectation of b squared equal to this expectation of b squared equal to b squared. Expectation of any constant is equal to constant itself. All right? So, what is this? This is mu x. So now you can see that b squared here, we expand this one, I also have b squared, so cancel out. And then this 2ab mu x, we also cancel out. So left with only two terms. A squared expectation of x minus a squared mu x squared, which is, I take a squared, so it becomes a squared times variance of x. So you can see that you multiply a random variable by a and add a constant. The mean will be a times expectation of x plus b. All right? But while the variance, by adding a constant here to the new random variable, will not change the variance. In other words, variance of a random variable plus b is equal to variance of x. I just put a equal to 1 and b still there. All right? So it's the same as variance of x plus b equal variance of x. That means adding a constant to the x. That means each x value you just shift by b. The variance will be the same. The variation among all the x will be the same. Only the mean will change by shifting the b. All right? So this is how we prove it. Variance of ax plus b equal to a squared times variance of x. We only apply to this form, ax plus b. So let's look at an example. So here is an example. So we have this jewelry shop. Okay. Purchase 3 necklaces, $500 each, and sell it $1,000. But if you don't sell it, you can sell back to the designer at $200 a piece. That means you make a loss of $300. All right. So now we have 3 necklaces. So we buy it, each one we spend $500. We sell it at $1,000. And if unsold over a certain period, a specified period, then the manufacturer or the designer will back at $200. They pay $200 to get it back. So of course, we are interested in what is the expected gain. All right. So what's the random variable here? All right. You have the number of necklaces, and all this, how much you gain, how much you lost, basically depends on the number of necklaces that you sell. There are only 3. You can sell 0, 1, 2, or 3 because you only have 3. So that is the x. So x is the number of necklaces that's sold. And x takes the value. You don't sell any, 1, 2, or 3. All right? And we are given. So in this case, we don't have to work out the probability function. In some situations, we need to work out the probability function. But in this case, we are given the probability function. So the chance that you sell 0 is 0.1, 1 is 0.2, 2 is 0.3, and 3 is 0.4. Oh, so it's a table form. Can we express this in a formula? Do you see is it possible? All right, so for this particular example, f of x equal to 0.1 times x plus 1, where x equal to 0, 1, 2, and 3, and 0 otherwise. Check whether this is the same as the one given in the table. So when x equal to 0, it is 0.1. When x equal to 1, it is 0.2, and so on. All right? All right. So we have everything. We know the probability function. So we know everything about the behavior of this random variable x, which represents the number of necklaces sold. All right. So now we are asked to find the expected gain and the variance of gain. So gain is a random variable. How much you gain depends on the number of necklaces that you sold. All right. So we want to find the expected gain and the variance of the gain. So first of all, we have to work out what's the gain. So x is the money that you got is a function of the number of necklaces that you sold. So therefore, g of x is the number of necklaces sold. It depends on the revenue minus cost. That is your gain. So the revenue will be 1,000 times x. That is the money that you get. If you sell 0, you don't get any revenue. You sell 3, it's 1,000 times 3, you get $3,000. And what's the cost? No, not finished yet. All right, this is still part of your revenue. All right, so if this is the x is the number that you sold. The number that unsold is 3 minus x. So for each unsold one, you will get $200. Am I right? Right? So x is the number of necklaces you sold. If you sold 0 necklace, then you won't get $1,000. But all the remaining 3 unsold, you will be sold back to the designer with $200 each. So it's 200 times 3 minus 0. So this is represent the revenue. All right? Then the cost. The cost is a constant. It doesn't matter how much, how many necklaces that you sold. You have to pay $500 each, and for 3 of them. So it's 3 times 500. That's the cost. So simplified it is 800x minus 900. All right? So it depends. So you can see that from here. You know that if you sell 0, then you lost $900. If you sell 1, you lost $100. If you sell 2, and you gain $700, and so on. All right? So we are asked to find the expectation of gain. That means we want to find expectation of Gx. So this is the Gx. This part is the Gx. All right? And then times the f of x. So you substitute and then get it, and the answer is 700. So you expect to gain $700. But it does not mean you will get 700. You just expect to get 700. You may get either, how much? Either you lost $900 or lost $100 or gain 1,002. So 1,600 or 1,600 minus 900. So it is and 3. So 2004, that means 1,005. All right? So you can think of it like this. You will gain when x equal to 0, 1, 2, 3. So your gain will be minus 100. All right? minus 900 minus 100, and then when x equal to 2, so it's 700, and x equal to 3, then it will be 1005. So these are the amount of gain. And then the corresponding probability of gain, f of y. Y is equal to 800 x minus 900. Then the probability will be according to, when you get this one, means x equals 0. So it's 0.1, 0.2, 0.3, and 0.4. So basically what we did here is just minus 900 times 0.1, minus 100 times 0.2, 700 times 0.3, 1005 times 0.4. All right? So you can also get the variance of Gx. All right. So by looking at the expectation of square of Gx, which is this number, minus the square of the expectation. So it's 640,000 for the variance of gain. Wow, a big number. So that's why we want to take the square root to convert it back to the ordinary scale instead of square. So we take the square root, it's 800. So it's still a big number. So the variation is a big number relative to the magnitude. Think of it, the standard deviation is 800. Compare with our expectation, which is 700. So you can see that the variation is a lot. All right. So in other words, you may fall, if you want standard deviation from the mean, already negative, in the negative range. All right. So this simply means that the variation relative to this one is quite big. All right. Let's look at another example. This is for continuous. So we have this PDF and find the expectation of x and the variance of x. I think you can work it out yourself. All right. So nothing. Okay. Let's look at this example 6. So x represents something which we did not specify, but y represents the number of days. All right. The patient stayed in the hospital. It's x plus 4. All right. While x has the probability density given by this. All right. Now, let me repeat it. I did not give an interpretation of x, at least in the question, in the example. But y is defined as the hospital period, the period that you stay in hospital for a certain patient. All right? And this random variable y follow the PDF, not y, but x follow this PDF. So we are asked, what is the expectation, average number of days stayed? All right. So we are asked to find the expectation of y. All right. Now, if you notice that y is a linear function of x, it is in the form of y equal ax plus b. So expectation of y is equal to a times expectation of x plus b. So you may just work on the expectation of x. All right. So to find this, so there are two approaches to find. We are asked to find the expectation of y. One is treat y equal expectation. So y treated as a function of x. All right. Then what I do is to integrate x plus 4. This is function of x times f of x dx over the range from 0 to infinity. All right. So this is one approach. Treat this y as a function of x. So it's the function of x times the PDF of x. What's the second approach? The second approach is to work on the expectation of x. After that, I add 4 to it. So in that case, this is the expectation of y. So I can work out the expectation of x, which is integrate all right. This is expectation of x. After I got the answer, I add 4 to this answer. Both should give the same answer. Which one is easier? The first one or the second one? Now, usually, it is finding the expectation of x is easier. But in this particular example, finding expectation of y is easier. Why? Integrate x times 32 over x plus 4 to power cube. To do that integration, you have to do some more work. Well, the expectation of y, the x plus 4 happens to be the same as the denominator. You can do the cancellation. All right, it makes it much easier, right? But this is not from statistical point of view, they are the same. Whether you get expectation of y first or get the expectation of x, then add 4 to it, it's the same. Only the calculation, do the calculus part. All right. If you understand or you know the trick, you will have an easier time to get the answer. But if you are very good at your calculus, it doesn't matter which way you do it, you will always get the same answer. All right, this is what I used. All right, so I get the answer 8. Okay? All right. By the way, do summation may be easier. Do integration, you have to be careful when you do the integration, how you substitute the limits. All right? And I have to stress, the definition of expectation is like this. But you must pay attention to the PDF. It may take different form for different regions. So your integration, you have to separate into a few integration. All right? So that's important. All right. Last session of this chapter, Chebyshev Inequality. It basically, all right, a lot of time you need to answer the question, what is the probability of x less or equal to certain constant, let's say. If you know the PDF or probability function, you can easily work out this one. That means with knowledge of f of x. Or for example, I want to know what is variance and expectation. If I know this one, I can easily compute this too. All right. So now, the other way around. So suppose I'm given expectation of x and the variance of x. That means I don't know the probability function or the probability density function. I only know two numbers about this distribution, the expectation of x and the variance of x. I want to compute certain statement about probability of x. For example, x lies between minus a and a. All right? Can I do that? Just given these two numbers, not this PDF or probability function. We don't know. We just know these two numbers. Is it possible for us to compute this probability of x between two numbers? And the answer, of course, no. Sorry, we cannot. But although we don't know the answer, but we can give a bound. All right? That means this number may be bounded. All right? In fact, this is absolute of x less than a. So it may be bounded below by some number. By some number. That means I cannot tell you the answer, but at least I tell you what is the bound. All right? So that is what we call Chebyshev inequality. Chebyshev is a Russian mathematician, so he proved, or at least he have this result, saying that, okay, if you know the expectation, remember, you know the expectation, x and the variance of x, or standard deviation of x, then you can answer the question, what is the bound for probability of x within certain range? All right, so this is what we do. So, this is the result. All right, given x, expectation of x equal mu and variance of x equals sigma square, then for any positive number k, then the chance that x falls within or bigger than k sigma away from mu. First of all, what does this mean? So first of all, you have to understand x minus mu greater or equal to k sigma means that x minus mu greater than k sigma, or k minus mu less than minus k sigma. All right, either one is equivalent to this one, x minus mu less than k minus k sigma. So what it means is like this. This is mu. So this is the x. All right, this is PDF. So x minus mu, the absolute difference, is greater than k sigma. So this one is mu. Okay. So in other words, I want x to be here or x to be here. All right. The opposite of it is x minus mu within k sigma. Right? Within k sigma. Oh, okay, less than k sigma to make it. So x minus mu within k sigma. So this part is k sigma. This part is also k sigma. But this value is mu minus k sigma. This value is mu plus k sigma. So that means x falls within mu plus k sigma and mu minus k sigma. This probability. All right? We want to find out this probability bound or outside it, which is 1 minus it. So Chebyshev inequality stays in this way. It says that, okay, the chance of x falls outside k standard deviation from the mean mu, all right, both greater than or less than, the chance cannot exceed 1 over k squared. It gives a bound that, okay, your x outside this range of k standard deviation from the mean. This translates in English means that k standard deviation from the mean mu. This is mu, k sigma. So this point is mu plus k sigma. This point is mu minus k sigma. Beyond that, that means these two parts. The chance that it falls here and falls here is less or equal to 1 over k squared. All right, so, or alternatively, you can say that within this k sigma, it is 1 minus this number. 1 minus 1 over k squared. To make sense, k, what happens if k equal to 1? So, within one standard deviation, the probability must be greater or equal to 1 minus 1 over 1, which is 0. The whole thing is 0. Anything wrong? Nothing wrong. All right? It simply means that it's useless when k equal 1. So what happens if k equal to 0.5? Wow. K equal 0.5. Then what do we have for this number? Negative. 1 minus 1 over 0.5 squared. So 1 over 0.5 squared is a number bigger than 1. 1 minus a number bigger than 1 is negative. Oh, but this is a lower bound. Hey, without this Chebyshev inequality, I always know that probability of certain event must be greater or equal to 0. Of course, it must be bigger than 1 minus 1 over 0.5 squared. So my point is this inequality works for any k, so long as it is positive. It may not make much sense if k is less than 1. So usually we apply to k bigger than 1. Let's say k equal to 2. That means what is the probability of x lies between two standard deviation from the mean, mu? That is 1 minus 1 over 2 squared. So the answer is 3/4. So we know that for any distribution, the chance x, all right, falls within two standard deviation from the mean, the chance must be at least 75%, 3/4. So that is the Chebyshev inequality. All right? So just to summarize, this inequality helps us to calculate the probability of x falls within a certain standard deviation from the mean. Give us a bound. All right? It does not give us the exact value. And in some situation, the bound is really, really off. All right? It does not make sense. So for example, k equal to 0.5 is useless. Even k equal to 1, it also won't help. All right? All right. So, and this inequality applies to all distribution. And k has to be positive. Remember, k has to be positive. Don't apply to negative. Okay, so it gives a lower bound for x minus mu within k standard deviation. It's interpreted as x minus mu minus k sigma. Between minus k sigma and k sigma. I hope you understand this one. A less than b means that A is between b and minus b, where b is positive. All right, that's the definition of absolute value. Absolute of A less than b, that means A is between b and minus b. All right, so here's an example. X follows certain distribution, and we only know that expectation of x equal 14, and where standard deviation of x equal to. So what is the probability of x between 7 and 21? So you can see that the mean is 14. So I minus 14. So this one becomes 7, and this one becomes minus 7. So it's equivalent to x minus 14 is less than 7. And 7 is 2 times the standard deviation. So I can choose k equal to 2. Oh, this is exactly what I want. So minus, all right, minus the mean, 14. All right, so it becomes 2 standard deviation, 2 standard deviation. So it's greater or equal to 3/4. All right, now, nice, huh? Well, how about this one? So it's equal to x minus 14, then this is 7, this is minus 8. So should I write it as probability of x minus 14 less than 2 standard deviation? Then I miss out something. This is not minus 7. Or write it as 2.33 sigma. You see? This one is minus 2.33 sigma. This one is 2 sigma. So it's x between 2 sigma and minus 2.33 sigma. So I ask, what is this probability? I cannot get the answer. But I can give a bound, a reasonable bound. So now the question is, should I convert it into x minus mu? Mu is 14. X minus mu less than 2 sigma, or x minus 14 less than 2.33 sigma. Which one should I use? You understand what I'm trying to do, but I still have to make a decision. Okay, because the two limits are not of equal, the k is not the same. For k sigma, the lower bound is not k sigma, but, okay. So my problem now is I have this result, k2 and this is K1. All right? So K1 sigma and K2 sigma. And K1 and K2 are not the same. This I put a minus. K1, K2 are not the same number. So should I use, in this example, use 2 sigma or 2.33 sigma? But if you understand the argument so far, it's very obvious. This one must be greater than this number. All right? But if so now, what can I say about this probability? Compare with this probability. Is it obvious? Can I say that this one must be greater or equal to this one? Hey, yours is from 7 to 21. Mine is from 6 to 21. I have a larger range. All right? I don't know whether that was non-zero probability, but it must be bigger. At least get what you have. Because this is a subset of here. So this one is bigger than this one, so it's bigger than 3/4. So at least I can tell you, yes, this, what you asked for, I don't know, but I know at least it's equal to 3/4. All right? Now, but on the other hand, if I treat this as 2.33, all right, then I will get, I still can work out, all right? But then your bound will be smaller, all right? Which is not very, very good. Okay? Now you try that. All right? I say 6 to 21. Try to get this part. So I'm arguing this one is bigger than this one, so my bound is 3/4. All right? So how about if I increase? So this one, all right, I choose 2.33 sigma, which means that I'm looking at probability of 6, x, and 22. I look at this one. This one is 2.33 standard deviation. So if I work on this part, which is x minus mu 2.33 sigma, so I can get a bound which is 1 minus 2.33 square. All right? Or 2.33 means what? 7 over 3 square. So it becomes 7 over 3 square. 1 minus it. All right? But the bound that you get may be smaller. All right? It's a bit confused now, but you have to able to answer the question, what happens if the range given to you is not symmetrical about the mean? How do you deal with it? All right? This example I gave you, I do the easy part. This one is symmetric. These two numbers, 7 and 21, is symmetric about the mean. All right? So what happens if it's not symmetric about the mean? Then what to do? So you have to understand the argument. We are working on the bound, the lower bound, or the other one is upper bound for x outside the range. All right? Here we work x within the range. How many standard deviation within the mean? So it's the lower bound. So from that, you have to decide on how you adjust. All right, here's another example. We are given that this is the probability function, all right, and expectation of x and the variance or standard deviation is 1.54. So by applying the Chebyshev inequality, the chance that x within 2 standard deviation of the mean, outside 2 standard deviation of the mean is 0.25. This is applying the Chebyshev inequality. The objective is to show that what is the true values. What is this probability? All right. Now, I can compute the exact probability because I have the PDF. Sorry, I have the probability function. So I can compute the probability. So this simply means that x is less than, this means that x is less than mu minus 2 sigma, or x is bigger or equal to mu plus 2 sigma. But what is mu minus 2 sigma? mu minus 2 sigma, all right, is minus 0.44. And mu plus 2 sigma is 572. So now I go back to look at what's the x, the chance of x less than minus 0.44. So minus 0.44 is here, minus 0.44, which means that you have zero probability of x less than minus 0.44, right? And the other one is greater or equal to 5.72, greater or equal to minus 5.72. So it must be somewhere here. So x greater than 5.72 is equivalent to x equal to 6 in this example. So these two events are the same. While x less than minus 0.44 means that x, all right, okay, there are no x value. So the probability of this one is equal to 0. All right? So we add up these two probability, so it turned out to be 0.04. So this example to tell you that the exact probability of this x outside two standard deviations of the mean for this particular probability function is only 4%. While if you apply the Chebyshev inequality, it only tells you that, okay, this probability must not exceed 25%. So you can see that there's a lot of difference between the two. But of course, 1/4 is still better than if you don't know anything. Although the correct answer is 1%. But here we have 25% from the Chebyshev inequality. All right, so the Chebyshev bound is too conservative. All right, okay. I still have a few minutes. Let me just prepare you for a tough ride for the chapter 3. All right. You see, chapter 2, we're dealing with one variable or a function of that random variable. All right. Chapter 3, we are going to deal with at least 2 random variables. All right. So 2 random variable has more work than double the 1 random variables. Okay, why? Because there are association between the 2 random variables. All right, so they jointly behave. That one, you have to look into it. So in other words, when we look at this 2-dimensional random variables, you have to consider x, consider y, and consider x, y together. That is a hard part. All right. So what we are going to do are the following. Let me. So 1 random variable case, 1-dimension random variable case, we talk about random variable and f of x. So we talk about expectation of x, we talk about variance of x, even expectation of function of x, and so on. 2-dimensional random variable, we talk about x and y. So that means for each individual unit or experimental outcome, there are two characteristics that for the same individual. All right. So a simple example is height and weight for an individual. So instead of just looking at the weight as 1 random variable, now we look at together, weight and height together. So each individual will give you 2 characteristics, weight and height. All right. So then it's represent together. This is a function. Now it's a 2-dimension function. 2-dimension function involve x and y. All right. Then we talk about expectation of x, variance of x, expectation of y, variance of y. So these are okay. One more thing. We talk about something called covariance of x and y. This is to measure the behavior of x and y together. This part is an additional one. All right. So we have expectation of x, variance of x for 1 for the x. We have expectation of y and variance of y for y. But we also have to put these two together. That's called covariance of xy. This is the way that we try to describe the joint behavior of x and y. All right? Then, so what happens if one variable has nothing to do with the other variable? That is the concept of independence. So we talk about independence of x and y. In fact, we also have, from here, we have marginal PDF or marginal. All right? That means we just look at x only, forget about the y, and look at the y only, forget about x. And unfortunately, if you remember in chapter 1, we also talk about the conditional probability. So it just expressed in terms of random variable. So these are the few things that we are going to cover. All right? So the tough is quite tough. It's the concept, because now we have more things involved. And not only that, your calculus, your summation or integration getting harder. All right? Because you are dealing with two variables. All right? Some of you may have never learned about doing double integration, but basically that's not very crucial in this part, but you just do it one by one, just like a partial differentiation. You integrate one variable first, treat the other variable as constant, do the integration, and after that, you do the integration again with the other variables. All right? So I've already uploaded the notes, and I think I also upload tutorial 4, right? Tutorial 4, which is for tutorial 5, 4. 4 is for this week, right? 5. I upload tutorial 5 for next week, right? Is it? Yeah, I think I upload. And also, I upload the solutions for tutorial 2. Both 1 and 2 are supposed available now. All right? And 3 later. 4 later. All right? I want to give you time to work out those who have not done. All right? So if you have done it, you don't need the solutions. All right? You need the solution, but I give you more time to do your tutorial problems, even after the tutorial. Oh, you need that, right? If you have not done it, you have to do it. All right. Okay, so we stop here. Yeah, remember the midterm test, week 8, Tuesday, right? Tuesday evening, 8 o'clock.